Hello again. This is Math 1120 coming to you from the College of DuPage. The title of this lecture is Pressure, Pascal's Principle, and such. And I remind you to be an active learner while you're watching this video. We're going to talk about volume, stress, and strain first. When you dive underwater, the water exerts nearly uniform pressure everywhere on the surface of you and squeezes you into a slightly smaller volume. This situation is different from other kinds of stresses and strains that can be talked about. The stress is now a uniform pressure on all sides of you, and the resulting deformation is a change in your volume. We use the terms volume stress and volume strain to describe these quantities. Another familiar example is the compression of a gas under pressure, such as the air in a car's tires. We use the terms volume stress and pressure interchangeably. As you recall, the pressure in a fluid, denoted by lowercase p often, to distinguish it from power, which often is capital P, is the force perpendicular. That's what this F sub perpendicular symbol means. F perpendicular per unit area, transmitted across any cross-section of the fluid against a wall of its container or against a surface of an immersed object. Now, if the force is not perpendicular, it's at an angle, trigonometry comes into play. So here's the equation. The pressure is the perpendicular force per unit area. When an object, a solid object, is immersed in a fluid and both are at rest, the fluid exerts forces on the surface of the object that are always perpendicular to the surface at each point. If they were not, the fluid would move relative to the object. When we apply pressure to the surface of a fluid in a container, so here we're applying pressure, there's an area, and we're putting a force perpendicular to that area, such as a cylinder and piston shown here. The pressure is transmitted throughout the fluid and also acts on the surface of any object immersed in the fluid. This principle is called Pascal's Law, named after the French mathematician Pascal. If the pressure differences due to the differences in depth within the fluid can be ignored, and in the problem that I assigned you they can't be ignored, they're different, but here I'm saying if they can be ignored, then the pressure is the same at every point in the fluid and at every point on the surface of any submerged object. Again, the force applied to the piston is distributed over the surface of the object, and at each point on the object, the force is applied perpendicular to that object, and you see the force is going to be P times A, since P is equal to the force perpendicular divided by A. So at each point in the object, the force applied by the fluid is perpendicular to the object's surface. Now, pressure has the same units as stress, and commonly used units include 1 Pascal, which is 1 Newton per square meter, or 1 pound per square inch, or sometimes this is abbreviated PSI, pounds square inch. Also in common use is the term atmosphere, abbreviated ATM. 1 atmosphere is defined to be the average pressure of the Earth's atmosphere at sea level. 1 atmosphere then is approximately 1.013 times 10 to the 5th pascals, or in terms of pounds per square inch, it is 14.7 pounds per square inch. Students should note that pressure is a scalar quantity, not a vector quantity. It has no direction, although the force applied does have direction. We noted that pressure plays the role of volume stress in volume deformation. So the corresponding strain, called volume strain, is defined as the fractional change in volume. That is, this is the ratio of the change in V, delta V, to the original volume, V0. So you see, if you're applying these pressures, and these are the pressures perpendicular to an object, it can, depending on the elasticity of the object, crush the object a bit. And so what you have is an initial volume, V0, at initial pressure, P0, and a final volume, V, at the new pressure, which is P plus P0 plus delta P. Delta P is the change in pressure. And we, in fact, define that ratio to be the volume strain. So it's delta V divided by V0. Now, there are no units on this volume strain. It is a scalar because if I had meters cubed up here divided by meters cubed, the meters cubed would cancel out. Now, delta V is equal to V minus V0, where V is the final pressure, is the final volume rather, after the pressure has been applied. Delta V is always negative when pressure is applied. In the problem that you're doing in the low stakes assessment, pressure is actually released at the surface of the water. And these concepts can be used when we're weighing things. In a supermarket, for example, often a vertical spring inside this produce scale stretches when fruits and vegetables are placed in the pan scale. A gear mechanism converts the stretching motion of the spring into rotational motion of the dial. Within reasonable limits, the scale's internal spring obeys Hooke's law, and the downward displacement of the spring is simply proportional to the weight in the pan. This simple yet effective apparatus gives shoppers a fairly accurate measure of the weight of their produce before they enter the checkout line, and they weigh them separately there. When Hooke's law is obeyed, the volume strain, which we defined before, is proportional to the volume stress, the change in pressure. The corresponding constant ratio of the stress to the strain is called the bulk modulus. This is also in your low stakes assessment, so expect to use this equation, and that's denoted by capital B. So when the pressure on an object changes by a small amount, delta P, going from P0 to P0 plus delta P, and the resulting volume strain is delta V over V0, then Hooke's law takes the following form. B, which is the constant associated with the material being compressed, delta P is equal, B, the constant, is equal to delta P over delta V divided by V0. This is an important equation for the problem I ask you to do. Now the units here are going to be, since delta V over V0 has no units, the units on capital B are going to be the same as the change in pressure. That's going to be pascals or newtons per square meter. Some notes. The negative sign ensures that B is always positive, and delta P is equal to P minus P0, where P0 is the pressure corresponding to V0. And again, this is most useful, this equation, in solving one of the low stakes assessment problems due soon after Thanksgiving. And in fact, here's an example that's similar to that one. In the problem in your book, we had oil, but here we and an oil spill, but here we have water. So we're going to look at the volume deformation of water. Now, the bulk modulus of water is 2.2 times 10 to the 9th pascals. And a pascal, of course, is a newton per square meter. By how much does a cubic meter of water decrease in volume when it's taken from the surface of the ocean down to the depth of 1.0 kilometer, where the pressure is this, 9.8 times 10 to the 6 pascals. And that's greater than it is at the surface because the depth of water adds things. This is very similar to the problem that I asked you. So we're going to use this equation about the bulk modulus, and we're going to solve this for delta V. So delta V is going to be minus delta P V0 over B. You should perform this algebra to make sure you understand it. And the change in pressure is going to be this, because this was greater than, so that was the whole change in pressure. And that may be a little bit different in the problem that you're working, but this is the change in the pressure. It was the volume was 1 cubic meter, and this is the bulk modulus. So we plug all those numbers in, and we get that the volume decreases by 4,500, and this should be not square centimeters, this should be cubic centimeters, because this is a volume. It is interesting to note that many parts of your body are very strong. Here is the breaking stress in pascals used to break various kinds of metal, brass, glass, and steel, and wood, and so on and so forth. But if you look, your arterial wall is pretty strong. Not as strong as aluminum, but still pretty strong. You've got to have a lot of newtons per square meters to actually break that. You have similar things for bones, and notice that bones can almost be like aluminum. It ranges from 1 to 2 for bones, and you can see there's also collagen, which is some of the tissues that you have with your skin, is also reasonably strong. There's one more application that we want to talk about of Pascal's principle, and that is hydraulic machines. I have asked questions like this on the final exam, so please pay attention. So now we're going to consider what happens when we change the pressure on a fluid contained in a vessel. So here is the fluid contained in the vessel, and this fluid is not being compressed. So what happens is, consider a horizontal cylinder with a piston and 3 vertical tubes at different points. So you see here's a tube, and this is a tube as well. The pressure in the horizontal cylinder is indicated by the height of the liquid column in the vertical tubes. It is necessarily the same in all. If we push the piston, the fluid level rises. So if we push on this piston, the pressure is downward, and it raises this on this side. The fluid level rises in all tubes, and it reaches the same level in each one of them. Now this indicates that when the pressure on the cylinder is increased, it is distributed uniformly throughout. We can say that whatever external pressure is applied on any part of a fluid contained in this vessel is transmitted undiminished and equally in all directions. That is Pascal's law. This is Pascal's law for transmission of fluid pressure, and has many applications in daily life. And so what happens is, here you're pressing on this piston that has area A1, so you're giving a force of F1 on A1. It's transmitted through the fluid, and it manifests over here in area 2, which is shown to be a bigger area, and force 2. So a number of devices, such as the hydraulic lift and hydraulic brakes that are in your car, are based on Pascal's law. You see, you don't have to press on your brakes so hard to stop a car, even though the force is magnified. In these devices, fluids are used for transmitting pressure. In hydraulic lift, as shown in the figure, 2 pistons are separated by the space filled with a liquid. Okay, so this is a non-compressible liquid. And this is what is true. The pressure over here is the same as the pressure over here. So F1 over A1 is equal to F2 over A2. And that means I could solve for F2, so F2 is equal to A2 over A1. Now this can be a multiplicative factor. Here, for example, the area here is smaller, So you can push down and you actually use the hydraulic to perhaps even lift a car. So F2 is equal to A2 over A1 times F1. So here's a problem. So suppose, and I'm repeating some things, I'm just reading the problem. Hydraulic systems utilize Pascal's principle by transmitting pressure from one cylinder, called the primary, that's where you're pushing down, to another called the secondary. This is the one that's lifting the car. Since the pressure will be equal, if the surface areas are different, then the forces applied in the pistons will also be different. So suppose in a hydraulic lift, the piston of the primary has a diameter of 2.25 centimeters, and the piston in the secondary has a much larger diameter, 26 centimeters. Now this is diameter, not radius. What force in newtons must be exerted on the primary cylinder of this lift to support the weight of a 1,750 kilogram car? That's supposed to be a large car resting on the secondary cylinder. Well, okay, so we know F1 over A1 is F2 over A2, and so F2 is A2 over A1, and this is F1. Now, as you're plugging in here, you have to think about what's going on, and we were asking how much do you push on the primary cylinder. So you see, this is going to be, the force then is going to be, now we could put the we could put the we put the A2 on top, but you see this was the force that we had on the lower piston, so that's the one that's on top, and this would be the area, but the area is proportional to the square of the diameter. Pi is just a constant, and the 4 you get by squaring the radius is, in comparing it with the diameter, is also a constant. So you see those numbers will cancel out. So what we have then is this is just the ratio of the diameters squared times, and this was kilograms, so we have to get the weight. We wanted in newtons, have to take this times 9.8. So we would do this calculation, and we would get the answer to this would be 128.43. And you see we do get a very significant mechanical advantage by doing this. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless all of you.